Yes, this time let's take a look at how to optimize this variable size locator that I mentioned earlier. Now, last time, some of the drawbacks of this variable size allocator is in the time we allocated and released. Why does it take n hours? For example, when we were allocating, we said there were nodes like this on the connection list. These nodes hold the size and then the memory pointer, literally in this memory pool. So, you're going to have these data blocks that you can allocate. And each will have all this information, such as the size of the next data block, and then what is the start address. This information is organized into each node, and we manage it on this memory pool as a connection list. Then, when we want to do something to allocate now, we check these things one by one. For example, we want to allocate an O byte of memory, but this is 3 bytes, 10 bytes, 20 bytes, or 1 byte. If we say it, we will explore each node one by one to see where the data blocks of a size that can be allocated an O byte are. You have to find it. We had a disadvantage here that it took us time. Similarly, when we do free, let's assume that, for example, the size is 12, and then the memory is 0x, or some data of 0x. Then, now let's say these 4 blocks of data existed. If this is young x or young, this is young x, young x, Leo young x, or Samyong, if we explore all 4 of these, what is this child named Li Young X Li Young? Where to go in memory order? You also need to find out where to go on this connection list. So if you look at it, Young Young Il Young is O Samyong. He can get in between. So we create a new node that holds this information, and then we add it in the middle like this. Of course, this process also includes all nodes on the connection list. Of course, in that you need to explore. It takes some time. In other words, in terms of blood sugar and release, there was a disadvantage that you had to explore every node on the connection liter in 5 times. At this time, this process of converting this error and time into error, log in time is optimization, and this method is. This is how we use a balanced binary search tree. Now, when we talked about what this balanced binary search framework is, we call this binary tree or binary tree. When we have a tree, all of these nodes are the largest. Having 2 self nodes is what we call a binary framework. And then the binary is the cutting frame, which is the binary search frame. It is just a data structure based on this binary frame. And when it comes to data structure for this search, generally, if it is smaller than the current value, it goes to the left or to the right. It is called a binary search frame. So usually in this binary search tree, we're usually log n. In other words, if I say there are 100 nodes, it means that if we were looking for a target, we would be able to find the target we wanted in just a log 100 of time. Now the important point here is, for example, it's a binary search tree, but there may be cases that are not balanced like this. So in theory, the log takes n hours, but in the end, in this case, we have to explore all the loads, so it can take 5 times n hours. This is a typical binary search tree. So, to prevent this, what we always do to make this tree balanced is what we call a balanced binary search tree. And there must be several types of this type, including the AVL tree and the famous red-black tree, but in my case, in this game engine. Two AVL trees are usually used. For an explanation of the AVL tree, I think you can refer to other materials a little more. But to give a rough explanation, let's classify various unbalanced cases. Well, the binary search tree that we balance in this way is this balanced binary search tree, and one of the many types is the AVL tree. And in this engine, we have optimized it by mixing AVL tree, this prelist, and allocator variable size allocator together. So let's finish this video for now.